Go.
Okay, let's get started. Okay, so it's Thursday. Either PS4 is due today or tomorrow. If PS5 will come out tomorrow, and so it goes. Any questions or problems? Yes?
So when we have a no parameter constructor, you say in the assignment that behaves as a constructor in which you pass a string that just contains 0?
Correct.
But doesn't it initialize everything to default values? So
Okay, what I said was, if I use the zero argument constructor to create a formula, that formula should behave just like if I created one with the string 0. Okay? That's not saying, yes, when I use the zero argument constructor, your instance variables will be nulled out. Nevertheless, if I create the formula and then call evaluate on it, I need to get 0 back. Okay? That means you got to change the value. Any other questions? So, about half an hour before class, I tried to push up something to GitHub, and it wouldn't let me. And I said, I'll figure it out later. And then, not 5 minutes later, a student came in the office, and it turned out it was this widespread problem, which seems to have resolved itself in the last few minutes. So, it was almost a Judy's Law thing when I blew it off when it happened to me. I think it must have been a GitHub problem. Okay, we're going to talk about a couple of things today. I'm going to start by talking a bit about UML. And UML, it stands for Unified Modeling Language. It's basically a bunch of graphical languages for creating models dealing with software. So, what does it mean to create a model, to make a model of software? Yeah?
It's like when we were drawing pictures of our object-oriented programming with boxes and arrows.
Okay. So when you draw stack and heap diagrams and show how objects refer to other objects, that's a model of the kind. It's a model of what's happening at runtime. Okay? Can you think of any other models that you've worked with? Yeah?
Flow chart for dealing with the steps of an algorithm.
Okay, so a flow chart is a model of an algorithm, sure. You got an idea?
You might want to get a detailed overview of the overall architecture of an application.
Okay, so some sort of overview. You know, in a sense, a Docker comment is a model of the method it documents or the class it documents. So we work with models all the time. It's just a form of abstraction. The goal behind making a model of something isn't to capture every detail about that something, because if you wanted that, you just look at the program. It's a way of capturing something you want to point out, something you want to emphasize. And just imagine if you're trying to explain to someone how your program works. You might go to the whiteboard or a piece of paper and end up drawing pictures. Those pictures you're drawing are models. And UML is just a sort of a more formalized way of drawing diagrams. And it's formal enough that there are software tools that can generate the diagrams and some that can interpret them. It's not clear to me that UML is used very widely in industry anymore. Every time I have an industry speaker in, I ask him, do they use UML? And he says they don't. Or she says they don't, depending on them. But nevertheless, bits of it are pretty useful. And so what I'm going to do is show you the basics of UML, of one portion of UML, and then use it to talk about the Spreadsheet project, which will sort of be an introduction to next week's assignment. So, it's a visual modeling language. It's language independent. It has lots of different types of diagrams you can create with UML. It deals with models, like I said, abstracted views of reality. So it's not as detailed as the program is modeling. So in UML there are structure diagrams which tell you about code, for example, and behavior diagrams which tell you what happens when the program runs. And I'm going to start just by quickly showing you some diagrams. I'm not going to explain what they mean. In some cases I don't know what they mean. But you can just get an idea. So this is a class diagram that models not a program, but the part of the world on which the program is going to be operating. So you see it talks about books and authors and book items and accounts and libraries and patrons and librarians and such. So this would be a UML diagram that models a library. It's a way of understanding how a library is organized, and then you might use this information to help write a program that automates library functions. So all the boxes and the arrows and the different annotations on the arrows and the lines all mean something. So, where this might have been created is, you've got a job trying to automate a library, and first you've got to understand how the library functions. So this models that. Okay? This is a model of an implementation, a different kind of implementation. So it has surface views and surface holder callbacks and activities and camera demos. So it's a model of the pieces of the program. These things are classes. And essentially it's showing you some of what what methods are inside the class, at least some of them, and how the classes interact, what the relationships are like. So that's another kind of UML diagram. All right? Here is a model of a different part of the system that sort of shows the business layer of an application, and the data layer, and the presentation layer. And here's the internal structure of a bank ATM. This is a component diagram. Let's talk about search engines and shopping carts and authentication. So I'm not familiar with this type of diagram, but it's the connectors all, it all means something. You could look up and read what it means. The diagram is useless unless you understand the notation being used. This is a use case diagram. So what would that be? What is a use case? Yeah?
How the end user might be using it?
Right. It's how a user, when you're considering a program, you think, how will the user be using it? And so every way in which the user might use your program or your system is a use case. And so this is just showing how customers and clerks and administrators and payment service all interact with aspects of your program. That's an information flow diagram that shows how information goes between different departments. All right, this is a sequence diagram. This is getting into the behavior of the program that runs, not just a static structure. But it shows what happens as they think of time as flowing down in this direction. And how messages are made and they're responded to in what order, and how it all works over time. We might use something like this, for example, to understand multi-threading. Okay? But we're going to talk about class diagrams. I'm going to, again, pretty quickly show you the basics of a UML class diagram. And then we'll look at a class diagram of a spreadsheet program where you're headed. So a box like that describes a class. And remember, it's language independent, so it's not going to look like C#. But the class has a name, it's employee. It has some attributes. You can think of them as instance variables or properties. The positions and salary are names of attributes. After the colon is the type, so position is a string of any length that's not 0. Salary is an integer. The plus and the minus is like public and private. And these are some operations. There's a method to give a raise. There's a method to change the years on the job. Now this doesn't mean that's all there are in the class. It's just saying that this is some of what's in the class. Just whatever the person who created the diagram wanted to emphasize. And obviously I didn't draw this by hand. There are actually tools in Visual Studio to generate class diagrams from existing programs or to create them from scratch, is where this came from. So that's a class. So you see these you'll see these in the diagram a lot. Okay? So these are two classes. You have a person class and an employee class that we just saw. So a person class has a name. Again, don't conclude that's all a person class has, a person object has, but we know it has a name. You see the person name is italicized. That indicates it's an abstract class or an interface or something like that. And, you know, what you call it depends on what language you're talking about. And this essentially means inheritance. That particular kind of arrowhead means that employee inherits from person. So you can capture the inheritance structure. Or maybe that employee implements person. We don't know if, it doesn't necessarily say that it's an abstract class or an interface or what have you. But it tells you something about the relationship between a person and employee. An employee is a kind of person. Okay? This is a line, a plain line like that. It's an association. So what that's telling you is, look at the label here. A client has contacts. Or I should say an employee has contacts with a client. And, okay. Help me out. Which way should I read this? I can't remember. Would an employee have, yeah, an employee would have customers, and a client would have contacts back in the company. Okay. So rather than say customers here as an attribute, you put it here on the line. And it's just a way of emphasizing, I mean, I could have just said plus customers, colon, client. But I chose to emphasize this relationship upon the class. Basically, the client is going to contain one or more references to employees, and employee is going to have 0 or more references to clients, is what it's telling me. I just chose to emphasize that relationship. Employee refers to clients, clients refer to employees. Every employee, well, an employee doesn't necessarily have any contacts with a client. It has to have at least, I mean, an employee doesn't necessarily have a customer, but clients have at least one contact with it. It's not a client. Yeah?
So what are those numbers where it says the employee deals with many clients? Is that kind of like the minimum number?
Yeah, this is saying, this number refers to employees. So it says a given employee can have 0 or more clients.
Okay.
And in the other direction, a client can have 1 or more employees. Yeah?
So this is something made with Visual Studio, not with UML? Or is this a UML example still?
Well, this is a UML example. And actually, I don't know if I made this a Visual Studio or another tool. I mean, I think I use some drawing tool. I suspect I use Visual Studio. But there are tools like Visio you can use to make UML diagrams. Okay, so that's an association, that line. And also, I should say, the association could be one way, in which case you put an arrowhead on it. So if the client didn't have any relationship with an employee, it would just go in this direction or be an arrowhead there. Then there's aggregation. This is an example, again, so this says that employee has offices. This is saying an employee has 1 or 2 offices, whereas an office only has 1 employee. So this open arrowhead is meant to say employee has an office. This implies ownership. Okay? And this is a different kind of ownership here, where this diamond is shaded in. So an office has 4 walls, any wall associated with one office. The idea here is, if we get rid of the office, the walls disappear. So the walls can't exist in the middle of the office. So that's why that's shaded in here. If we get rid of an employee, the office continues to exist. So it's a much stronger form of ownership right there. That up there, that dotted line, that dotted arrow just says the person uses a map. It may not be stored in an instance variable. It's just at some point, in some way, a person makes use of a map. So that's a dependency.
When you say a map, do you mean like literally like a map, or do you mean like a map data type?
I can't tell from the diagram. It just says map.
Okay.
If there were some properties or methods,
Okay.
we could tell, but I can't. Okay. So that's a very quick overview. My goal isn't for you to write UML diagrams. My goal is just for you to, you'll probably, it's not unlikely that you'll see class diagrams at some point. So it's nice to have some idea what it is you're looking at. And since the use I ever make of UML is to use it to talk to other people about programs, doesn't really matter too much if I get the arrowheads wrong or something like that, as long as I can use a diagram to get my point across. There's some other examples you can look to if you want to look at. In fact, we'll look at them. Spreadsheet project and a couple of object-oriented programming patterns. But this is why I was doing this, is so that we can actually use it on something that you understand, or at least are starting to understand. So this is the architecture that I intend your spreadsheets to have after PS6. So look at that diagram and tell me, given that crash course I just gave you in UML diagrams, what does this tell you about your ultimate implementation? And right now you have a formula class and you have a dependency graph class, and they don't have anything to do with each other. So this is showing how you're going to hook it all up into your programs. So read the diagram for me. Tell me what you can conclude. Yeah?
Spreadsheet along cell and dependency graph. If there was no spreadsheet, there would be no dependency graph in cell.
Okay, so the spreadsheet contains 0 or more cells. And I shaded that in to emphasize that a cell cannot exist independently of the spreadsheet. On the other hand, a cell is contained by only one spreadsheet. Okay? So spreadsheets are going to contain cells. Now, are these cells stored as a list, as an array, as a hash map, as what? Linked list? Can you read that from the diagram? No, it doesn't go into that level of detail. It's just saying that the spreadsheet is going to contain some number of cells. All right, that makes sense. What else can you tell from this? Yeah?
That a formula can't exist without a cell.
Okay, so a cell will contain one formula, 0 or 1 formulas, because there can be things in cells other than formulas. But one thing a cell can contain is a formula, and formulas aren't useful except when it's in a cell. So at least that's what the diagram is saying. Yeah?
There's only one dependency graph per spreadsheet, and each spreadsheet has a dependency.
Okay. There's a one-to-one relationship between dependency graph and spreadsheet. So you wouldn't expect two spreadsheets to share the same dependency graph. And dependency graph isn't really meaningful unless it's associated with a spreadsheet. Okay, so right off the bat, you know you're creating a spreadsheet. You'll be creating a spreadsheet class in PS5. Probably going to have a dependency graph as an instance variable to keep track of the dependencies among cells. And it's going to have a bunch of cells. And the cells will contain formulas. Okay? So, I'm not, what do we know about cells other than that they exist and they contain formulas? Yeah?
They can also contain strings or doubles.
Well, so that's a comment up there. And so I just hung that up there to say a cell could also contain, the contents of a cell can also be a string or a double. So a cell would either contain a string, a double, or a formula. Yeah?
They have names we can reference from other cells.
Okay, so when we talk about, you're noting that formula can contain cell names. So the variables in your formula are actually going to be names of cells. A formula can contain any number of cell names. And spreadsheet doesn't contain cell names per se, but the spreadsheet needs to know what cell names are. That's why that dotted arrow exists. Now, what about this thing right here where it says value, and this thing right here where it says contents? What's the importance of them? They're both private. Yeah?
Well, the value may or may not be a formula.
Well, the value the contents that may or may not be a formula. The value is something else. So, yeah?
The value may determine a cell's location in the grid.
Well, you're sort of, I don't see how you can extrapolate that from the diagram. You know that every cell has a value, it's not saying what the value is, and it has a content, which is either a formula, a string, or a double. So I've chosen to highlight that every cell has a value and a content, and it's important to understand the difference. And you can't tell from the diagram that there's a difference. But if I'm explaining the program like I am now, I can point and say, look, I thought it was important to emphasize that cells have values and contents. Let's talk about it. So what do you think is the difference between a cell's value and a cell's content? Yeah.
The value has been evaluated in some way.
Okay. The value has been evaluated in some way. Right? So we know, let's start with the content. The content's either a string, like hello world, or a double, like 3, or a formula. Yeah.
The contents are what's saved in disk, whereas the value is calculated on the fly.
Okay, so the value is what the user has entered in. I'm sorry, the content's what the user entered in. The user types, imagine using the spreadsheet. They say, okay, I'm on this cell, I want it to contain 7. So they type 7. So the content of that cell is 7. The value of that cell is what? 7. The user types the content as hello, the string hello. What is the value of the cell?
Well, that is whatever hello you evaluate to
Well, okay, that turns out that's a perfectly fine guess, but it's not right. There's no way you could know from looking at this. So if you set the contents of a cell to be a string, the value of the cell is that string. So in other words, the value is what's displayed when you just look at the spreadsheet. The content's sort of hiding behind determining what the value is. Now, what if the content of the cell is a formula? What is its value? What is the cell's value?
The evaluated formula.
It'd be the result of evaluating the formula. So when you look at my specifications, my detailed specifications for the spreadsheet class, value and content are not words I throw around casually. They're not interchangeable. They mean something. Okay? So you're building the spreadsheet in 2 phases, PS5 and PS6. In PS5, you're just dealing with contents. You're not even worrying about evaluating anything. You're just dealing with content, method. You're just dealing with the aspects dealing with contents. Then later on, in PS6, you'll deal with actually evaluating things. So it's important to keep these 2 words separate. Think about using Excel or something similar. Whatever you type when you're defining a cell, that's the content. What's displayed when that's evaluated, that's the value. So we got both. So the value is either going to be a number, which is either the number that was entered or the result of evaluated formula, or a string, or it could be an error message. An error is a value as well, like divided by 0 or something. Okay, what else can you tell? What's the relationship between dependency graphs and cell names? Yeah?
Every dependency graph, we can refer to, well, the dependency graph can refer to any number of cell names, but every cell name refers to the same.
Right, and it may be wrong. Cell name doesn't really have to refer to a dependency graph, but there's a cell name would only be contained by one dependency graph is the way to interpret that. So how is a dependency graph going to refer to cell names? Yeah.
By containing them inside of the dependency graph.
Okay. But I don't see cell names anywhere in your dependency graph right now. Your dependency graph maintains relationships between strings, right? Well, those strings, the actual strings that you use in your spreadsheet will be names of cells. Now, this doesn't mean you need to have a class called cell name or a struct name cell name. It could just be a string, right? I don't say what the methods are. Cell name might as well be represented as a string because no need making it more complicated than it needs to be. Okay, so imagine your dependencies, keeping track of the dependencies among cells. Now, where do those dependencies come from? How do we know that cell A1 depends on cell B3? Why would that end up in the dependency graph? Yeah?
Their formulas reference each other?
Right, the formulas, so if let's say, why would A1 depend on C3? Well, if A1 contains the formula equals C3 times C3, then A1 depends on C3. If C3 changes, A1 has to change as well. So for the PS5, you're going to be dealing with keeping those dependencies correct, maintaining the dependencies as contents change. PS6, you'll worry about evaluating the contents. So, you're going to have to, that sort of gives you some sort of roadmap. Now, there's one other aspect of this that we haven't talked about. What's the other big piece that's obvious in this diagram? Yeah?
Abstract spreadsheet.
Right. Spreadsheet abstracts abstract spreadsheet. So what I will be doing is I'll be giving you a class called abstract spreadsheet, and it'll have some abstract methods and some non-abstract methods, and you will work by extending that into your spreadsheet class. So any code that I put into abstract spreadsheet, you'll inherit. And I'm choosing to emphasize something. There is the hash sign means protected. There's a protected method called get cells to recalculate. And there is an abstract method called get direct dependence. So the one that's not in italics, get cells to recalculate, is one that I provide. But it calls get direct dependence. So get cells to recalculate is a key piece of implementation. It basically tells you if this cell has changed, what other cells have to be recalculated. And it implements a kind of a graph search algorithm to find all the cells that need to be recalculated. And it makes repeated calls to get direct dependence to figure out, to help it control the search. You have to provide get direct dependence. My method won't work until you implement that abstract piece. And this is what I want to head off. People will do that. Students will implement get direct dependence, and now my get cells to recalculate will operate correctly, and then they don't use it. They don't ever call get cells to recalculate. And if they manage to get the spreadsheet working at all, what they're doing is essentially re-implementing get cells to recalculate. Right? Get cells to recalculate is in there for a reason. It's for you to use. But it won't, it won't work at first until you supply get direct dependence. Then it will work. And then you should use it when you need to know what cells to recalculate. Okay, so that's a high-level overview of where you're headed. Any questions I could answer? It's also just your first exercise in looking at UML. Yeah?
You said value and contents were private. Is the dash in front of value and contents what signifies it being private?
Yeah, that means private, that means private. A plus, these little boxes are just ways to expand, and so I'm not talking about those. With that, and if I had a plus up here somewhere, it would be public, and that hash mark means protected. Yeah?
At what point during developing the whole spreadsheet program are we going to be moving from individual work to teamwork?
Okay, so after PS6, it's asking when do you move on to teamwork. After PS6 will come PS7. PS7 is putting a graphical user interface around the spreadsheet. That's your first pair project. And the way it's timed is PS6 will come due, PS7 will go out. The following week is a midterm, or the midterm. And then PS7 is due the week after that. So you've got 2 weeks to do it, but there's a midterm in the middle. But you want to have your pair picked out and ready to go before PS7 appears. Okay? Any other questions? Yeah?
Just on that midterm, are we going to know what's going to be on the midterm or what's going to be beforehand?
I'll have more to say about what's on the midterm as we approach it. Okay, I want to show you one more diagram. They're what are called classic object-oriented programming patterns. And a lot of them were defined by the so-called Gang of Four. 4 people that wrote a book about it 20 years ago or more, 25 years ago. But this is called the Singleton Pattern. And the Singleton pattern, here's a couple examples from Java. So there's a static, there's a runtime class. And if you, there's some methods on it that you need to use to control aspects of your program, how it's being executed. So the way you get the runtime object is calling this static method, get runtime. It returns a runtime object. Similarly, there's a security manager that controls, you can restrict methods. You could use a security manager to say, I don't want any I.O. to be executing. And then the security manager could veto any attempt to do I.O. If you want to get the security manager, you call get security manager. So my question is, why do we call get runtime a static method to get a runtime object instead of just calling the runtime constructor? Why do we call get security manager to get a security manager object instead of just calling the security manager constructor? Yeah.
The constructor itself is private and it's enforced that there's only one created.
Okay, so we said the constructor is private. The idea is, the key idea is, these are thought of as classes that you should never have more than one runtime object floating around. You should never have more than one security manager for your program. It shouldn't be possible to create two. It would sort of, the designers of the class decided that would be too confusing to have multiple security managers. So what we've got is, if you want the runtime object, you call get runtime, and it gives you back a runtime object. The method itself will create it. If you call it again, it'll give you the same one back. It just remembers the one it gave you last time. It gives you the same one the next time. That way you can never create more than one object. You can get one anytime you want, but it's always the same. How is that encoded into my diagram up there? What have I chosen to highlight about the Singleton pattern? Look at the attributes first. What does that tell you? What private instance variable would a Singleton class have? A Singleton object. In fact, I called it the Singleton. So when the unique Singleton object is created, it will be stored in that instance variable is the idea. Okay? Okay, what about the operations? You notice right here that the constructor is private, and there's a public method called getSingleton that returns a singleton. That code up there, I just realized is incorrect. That code should be for getSingleton. Since it's a picture, I can't edit it very easily right now. That comment is telling you how getSingleton works. So how does getSingleton work? Yeah?
If the singleton is null, it creates a new one, otherwise it returns the existing one.
Right. When you call the constructor, when you call getSingleton, which is supposed to, the first line is supposed to say getSingleton, it just looks, if that instance variable is uninitialized, it creates a singleton object, stores it in that variable, and then returns it to you. Next time it's called, it's just going to return it. It's not going to, it'll only call the constructor once. It's just forcing all requests for the object to come through the static method. Okay, so that's a Singleton pattern. And you see it, and you can read debates online whether it's, some people say it's not a good pattern, it's a bad pattern. It's not a example of what you should do, it's an example of what you shouldn't do. I'm not here to make that debate. I've created Singleton classes myself. I think it has its place. It's just to show you that when I want to highlight the essentials of the Singleton pattern, it's nice to have this picture to point at. I think I'll show you one more. There's something called the factory pattern that you run into all the time. So here's the idea. There are a couple, like calendar. The calendar class in Java has a get instance method. There are different kinds of calendars. Easier to explain up here. Suppose you have three related kinds of things. You have an abstract class called thing. And then you have different types of things. So for example, the encryption class in Java, or one of the encryption classes in Java, is implemented using a factory pattern. So there are lots of different ciphers you could choose from. but knowing how to use them correctly it's tough to know what parameters you would pass into constructors unless you are an expert. So what's done is we implement 3 kinds of things, maybe 3 kinds of ways of doing encryption. We hide these from our user. All the user sees is that class up there, the abstract class thing, and it provides a bunch of operations that are overloaded down here. So it's got operation 1, operation 2, they're overloaded down here. And then there's that method called getThing. And maybe what you pass to getThing is a string that describes, okay, I want a 100-bit cipher that has such and such a property. There's some way of specifying what type of cipher you want. And then getThing is smart enough to figure out what's the right way to instantiate one of these classes to give you back what you want. So you ask it for a thing, describe what you want, it figures out exactly which of these you need, calls the constructor, and returns it to you. You never call these constructors directly. So that getThing is called a factory. And you'll see that. And you'll find yourself wondering, why don't I have more direct access to these underlying things? It's because the designers decided it's too hard to describe how to make sense of these. It's easier just to go through the factory method to get an instance of the object when you want. So it's similar to the Singleton pattern in that you're going through a static method to get objects, but it's not Singleton in that you get a different one every time you call it. And again, picture just makes it easier to talk about what's going on. Okay, let's take a break and we'll look at all right, let's get started again. All right, I'll show you my program here. It's a prime number program. And what it does is it counts all the odd prime numbers less than whatever that number is, 14 million. So basically all the prime numbers other than 2. 2 just kind of was an outlier, so I didn't bother with it. Made my program simpler. And I'm just timing how long it takes to run. And that's it. Now I have a method here, count odd primes, obviously, and that's here. And it just calls a helper method called count primes in interval. So it starts at 1, and then it goes, this parameter says add 2 each time. So it goes 1, 3, 5, 7, and so on, up to max prime, which is at 14 million. And then down here, I'm printing out, it prints out what it's doing. But, it just loops through the interval and calls is prime, and there commits a count. And then it returns how many primes it found. And then there's an is prime method, which is another loop that looks at factors. So the details of the primality test aren't important. I just want you to understand that this thing here, it takes a starting point, an ending point, and then a delta that's added each time. So if I want to find all the primes, I start at 1, could start at 3, but I start at 1, and then go 3, 5, 7, 9. That'll get them all but 2. Okay? So let's run this and see how long it takes. There it pops up. I want you to look over here at this diagram. And you can see I'm using, some portion of my CPU. And at some point, okay, and there it finished. So if I bring this back up, you'll see it's finished. And it says 9107. It took 13 seconds and it found 910,000 primes roughly. Now, before it disappears, how much of my CPU was I using, do you think? That's gone. Yeah?
5%.
5%? Yeah?
12.5.
Yeah, I don't think, yeah, what do you think?
Well, assuming you're on a quad-core processor, you're probably maxed out a single thread.
So yeah, it was using, I've got 4 cores on here, and each core has essentially two virtual cores. So it was using all of that. So it used 1/8 of my processing power. I think that was about 1/8 of the whole thing. Okay? So what happened to the other 7/8? What if you're in a real hurry to get your prime numbers generated? And I've got this expensive quad-core computer on whose screen you can write, and I'm only using 1/8 of it to get my prime numbers. So that's, yeah.
One of those threads is busy dealing with user interface stuff, so
Well,
letting you interact with whatever it is you're doing.
Yeah, I mean, the cores are busy doing other things. It's running the operating system and it's running Visual Studio, and those, you saw the graph. Those the other stuff going on my computer wasn't very much, because it basically, I ran it, I run it again, and you'll see. So I start it up, and there it goes. It's up about that level. And then when it ends, you'll see it drops down basically to 0. There's not much else going on the computer besides counting computing primes. So, see? So, I'm not using much of my computer's capacity. So let me show you how to use multi-threading to do better. Here we go. This is called, that's not the one I want to do. This is called primes to task. 2 tasks. All right, so now my method, I call this method count odd primes to tasks. So I'm looking for the primes up to 14 million. And let's see what I do differently in here. I still call count primes in interval, but I'm calling it twice. Okay? I'm going from 1 up to max prime by 4s. So this call here is checking 1, 5, 9, 13, 17, and so on. This call here starts at 3 and goes up by 4. So it's looking at 3, 7, 11, 15. So they're not looking at the same numbers at all. Task.run, we'll back up shortly and look at more carefully what's happening. Basically what this says, what is this here? What are we passing to that run method? That's a delegate. So a task corresponds to a thread, and we'll talk about what threads are. We basically say, what this is going to cause to happen is that this delegate will be executed at the same time this delegate is being executed. And if we're lucky, the operating system and the runtime system for the language will run them on separate cores in my processor. So they truly do run in parallel. And if that happens, what should we notice? Yes? The CPU should be twice as high. I'll be using a quarter of my machine at that point. And probably it should take half as long, right? Because each task is only doing half the work that we originally did. So let me see if I can be fast about this. I'll click it. No, it didn't take. Oh, I got to change from primes 2 tasks to primes. Oh, that's right. That's right. So let's just go start. And the output doesn't matter so much, rats. Okay, so you can see it's using maybe twice as much, and look, it's already gone down to 0. So it ran twice as fast. I was able to use a quarter of the capacity of my computer. This is sort of the best case for parallelism. What makes this such a good thing to parallelize? Yeah?
Well, it's easy to split up the tasks and have it both be like constant, like both remain
Okay.
constant.
So it's easy to split up the tasks, and what were you going to say?
I was going to say that they'll never collide.
Right, they don't interfere with each other. That's the other thing. A lot of times you got things running in parallel, but they've got to deal with each other. And that gets complicated and slows things down. If they've got to collaborate as they work, they can't work completely independently. Here, they don't have to talk to each other. They just start, they run, it's done. Let me show you. Let's look back at the main method. No, let's look at this method. Now remember, what this method is supposed to return is the number of odd primes. So what's happening here? We fire off that task and it's running. We fire off that task and it's running. And then we return the result of T1 and the result of T2. The idea is, whatever is returned by this delegate is T1.result. So .result gets you the number that was returned by the delegate when it finished. And similarly with T2.result. How can we possibly execute T1.result plus T2.result after we just finished launching them? We've got to wait till they finish, right? We've got to wait the 7 seconds until they're both finished before we return. So how do you suppose this works? Yeah?
They run asynchronously, I guess.
Okay. You said they run asynchronously.
The return waits for both of them.
It waits, right. So when you call T1.result, it doesn't return. You won't get anything back from T1.result until the delegate's done. So this is a blocking operation. Now, how many threads does this program use? How many tasks, I should say, does this program use? Yeah, 3. It uses 3. The original, there's the one thread. Threads and tasks are kind of, task is sort of an abstraction on thread in C#, but when you run a program, you've at least written a singly threaded program. It runs, so that's one thread. So you've got the one thread that launched both tasks and is waiting for them to finish. And then you got a thread for each of these guys that's actually doing the execution. Now, how much of a processor is this thread using while it's waiting for the result? Yeah, basically 0. It's using a tiny, every now and then it'll check and see, is it done yet, is it done yet, is it done yet? But mostly it's just idling away. So that's why you don't see 3 processors work. Okay? So this thread blocks until T1 and T2 return. Then it gets the results added, and then the main thread, which eventually displays the result, comes back to life. So that's multi-threading in action, multitasking in action. Any questions so far about what I've talked about? How could we do better? Yeah, create more tasks. So I have one called primes in tasks. And if we go look at primes in tasks, okay, it calls count odd primes in tasks. What's it doing? Yeah.
So it looks like you pass in how many logical processors you have as n, and then depending on how many you have, it will just run
Okay.
it home.
So I'm passing in as the number of tasks I want it to split this work up into. And so it loops through and it creates, it splits up the search space the same way, different starting points. different intervals, creates them all, launches a bunch of tasks. Why does it store them in an array? Why do we declare that array tasks and store the tasks in them?
The test. Returning it.
Why do we need the tasks? Yeah?
We need to get the results later and something
Yeah.
like that.
Because as soon as we have fired all the tasks off, which we do up there, then we have to add up all the answers. And so I have a loop here that loops through the tasks, waits for the result. When it gets the result, it adds it to count and gets the next result. Now think about this loop right here. How will it, so we launch those tasks, the tasks take a while to complete, and so immediately it's going to hit this and it's going to stop, it'll block the task. So at some point in the future, this will become unblocked when whatever the first task was completes. Then what do you think will happen? It'll iterate, will it block again for 5 seconds or whatever? No, because probably by the time the first task finished, all the tasks finished. So what's actually going to happen is it'll wait a while here, and then it'll finish really quickly, probably, in return. So we got one task, the main task, or one thread, the main thread, that's waiting on all these tasks to finish. Okay, let's see how it works. And I'll definitely miss this if I don't click fast, but I'll. So we'll start it up. And
Whoa.
it's already done. Now, one thing I noticed was when I went to click and open that, to scroll so you could see what was going on, my GUI was very unresponsive. My mouse didn't work for a fraction of a second. What do you think happened?
All those scores count prime numbers.
Yeah?
Your computer didn't have any cores left over to deal with.
Yeah,
that,
I
so
was,
it waited till it
right, I was running so hard that, you know, the operating system, there are lots of things that want to run at the same time. Now, if you only have one core, and there's a bunch of things you want to run at the same time, what do? Those, I mean, there have been operating systems for a long time, and there's got to be multiple things running at the same time. How do you get the illusion, even when there's only one core, that you're doing multiple things at the same time?
Task switching.
Task switching? What's task switching? Yeah?
Kind of have the same core going back and forth between processes.
Right. So you've got a bunch of things you want to do. The operating system says, okay, you get to run for a few milliseconds or whatever, and then time's up. This one gets the processor, this one gets the processor, and they just rotate around like that. So most of the time, any given process isn't running. To you, the user, you're living in a different time scale. It seems like they're all running at the same time. So if you overload a machine, I created 7 threads, 7 tasks. I have 8 logical cores, 4 physical ones. I could have created 8, but I figured I wanted to leave 1 for, for other stuff. But even so, you saw it spiked. I was using about 3/4 of the, 7/8 of the machine, and at the end it spiked for whatever reason. Yeah.
So you left one core open, but your mouse still lagged. Is the operating system not smart enough to understand, oh, these 7 cores are going to be used for this. This one last core I'm going to use to...
Yeah, it's hard to say. It's hard to say why that happened. It's just that, except that the machine was overloaded. When you create tasks, that doesn't mean you're going to get a core for it. What you're doing when you create a task and start running it is you're asking the runtime system for the language, so it's basically .NET, to cooperate with the operating system and run them in some fashion. It figures out which processors get, which cores get to, which tasks, which threads get to use cores, which have to share cores. It does that scheduling. So the libraries we'll be using, you don't have direct control of that. Yeah?
So then you do shared core, would it be slower? Because you need to switch, you need to rotate, and there's going to be like a setting time for that. Although it's ignorable.
So if I created, instead of 7 tasks, if I created 16, it's not going to be any faster. In fact, it might be slower. Because now all these tasks are competing for the cores, and they're having to be swapped in and out, and that takes time. So yeah, that's a good thing to try out here. Let's go to
100.
You want to do 100?
Oh, no.
Watch the
No.
computer.
Let's see.
Don't make them computer crash.
Just let something.
I got to see where I call this thing. Okay. Oh no, I was wrong. I created 8 cores.
Okay, so that's why it's
Okay.
So that was 8 cores before. All right. So we're going to run with 100 tasks.
You might want to step away from the computer.
Step away from the computer. So I'll start it out, and it's still going, right? No, it never finished. Look at the green.
Yeah.
But that was, I think the original one was,
It spiked
Well-
at the end and dropped.
it didn't take any shorter time. I don't know that it took longer. Okay? So at some point, there's no, if you're trying to get performance, I can't do more than 8 things at a time.
Run with 7 and see if it doesn't spike.
All right?
Or see if your mouse doesn't drag.
Yeah, that's very subjective, the mouse drag bit. So I'll try 7. And here we go. Start. And it pops my display. Display takes a while to pop up. Okay, it's already done. So it's hard to interpret exactly what's happening, but obviously I'm using more of my machine than I was with one thread. Yeah.
So is there a way in C# to look up dynamically how many cores the system has?
All right. So he's asked, is there a way to look up how many cores, to have more control? And there may be. I have never tried to use it at that level. Clearly, if you're writing, if you're at a national lab and it's your job to get scientific computing algorithms to run as fast as possible, you're going to need to use a library different from the one we're using here. You need to have a low-level control over how things are scheduled, because that's a big part of the algorithm. But that's a complication we don't need to cope with. All right, so I'm going to step away from the code demo. I have more to show you, but I'll probably have to wait till another day. Let's talk about what threads are. I forgot to bring that up. So let me go back here. Okay. So you're used to writing singly threaded programs. Although, if you've ever written a graphical user interface, a GUI program, you've been using 2 threads. There's the main thread that starts the program, the GUI runs on its own thread. So you've done, in a very limited fashion, multi-threaded programming before. So think about what it takes to run your program. You've got to have one copy of the code. There's a runtime stack, right? You call the main method, a stack frame is pushed. It calls methods, stack goes up and down as methods are called and returned. While the stacks are while the code is running and the stack is growing and shrinking, your heap here is objects being allocated and deallocated and garbage collected. And so the program is running and managing memory. So there's one stack, one heap, and one program counter. So by program counter, just think of your single stepping through a program. And each time you step, a line of code is highlighted. You can think of that highlight as being the program counter. It's just deciding what's next, what's next, what's next. You hit a loop, program counter says, okay, go around in circles, execute these statements over and over again, and fall out the bottom, and boom, 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 boom. So you can trace, when you can trace the sequence of statements being executed in your program, that's a thread of control from beginning to end. So that's singly threaded programming. Okay? When you have a singly threaded program, and there's a core available for it to run on, it runs. And when there is not a core to run on, it suspends. And like I said before, the operating system, it decides. So it may let your program run for a while, and maybe after a while your program it stops itself while it's waiting for a file I/O operation. Well, the operating system is going to notice that thing's not doing anything anymore. Even if it has time left on its turn, it's going to take it out, remove it, suspend it, and let something that can make productive use of the processor run. So you're at the mercy. The OS decides when your thread runs. And the reason it's convenient to suspend a program is the code, the stack, the heap, the program counter can be stored in memory. And when it's time to start back up again, the suspended state's still sitting there in memory. All the variables still have their values, the heap still exists. The program counter hasn't budged because the thread wasn't running. And that's how singly threaded programs work. Yeah?
So I've heard that the stack is shared between all of the threads, and that the heap, that the heap is shared between all the threads, and stacks are thread dependent. Is that the case, and if so, why?
Yeah. Well, that's what we'll talk about right here. Okay, multi-threaded program. You have n threads instead of 1. You still just need one copy of the code. Why is that? Why doesn't each thread need its own copy of the code? Yeah.
They all share the same heap.
It has nothing to do with the heap so much. I mean, they all should, okay. All the threads can see the same copy. Yeah, so it's not the heap, they share memory. All the threads share memory, some memory. In particular, they can share access to the code. But what if one thread changed the code? Wouldn't that screw up the other thread? What if thread A decided, oh, I'm going to change the code?
What can't change the code?
Yeah, that doesn't happen. The code is read-only. Programs don't change their code. Now, you can write an assembly language program that changes itself as it runs, but any code that's generated by the C# compiler is not going to be self-modifying. All right, so they can all share the same copy because they can all see the same memory. There's each thread, well, I'll go on. Each has its own stack. So that means that this thread here has its local variables and parameters, and this thread here has its local variables and parameters, and this thread can't interfere with this guy's stack and vice versa. Okay? So they can be executing exactly the same method, but they've each got their own records of the local variables. Why is that a good idea? Yeah?
So if like running the same method, they'll have 2 copies of the same variable and they don't.
Yeah, they don't interfere with each other. It would be hard to imagine if you had to worry that your local variable might be reassigned at any point. It's hard to think about. So that you can be guaranteed, no matter how many copies you're running at the same time, no matter how many threads are running the same code, stacks can't interfere with each other. One thread can't mess with another object stack, another thread stack. On the other hand, there's only one heap. So if I've got a stack over here for one thread and a stack over here for another thread, they refer to the same heap. It's possible to have a reference from this stack to this object and a reference from this stack to the same object. It's possible for the 2 threads to refer to the same object on the heap. How does that strike you? Yes?
Like you'd have to be careful to know whether or not they're actually accessing the same object and in what order they do things.
Yeah, you have to be aware. When you multi-thread a program, you have to be thinking about how, in what way are they sharing objects? Which objects can be shared? Okay? It's hard. That's why multi-threading is hard, is because they share some memory. They don't share the stack, so we don't have to worry about that. But the stack can contain references to objects on the heap. The heap is the same. Why allow that at all? Why not just say every thread gets its own heap to eliminate this confusion? Yeah?
The heap can be really large and then have multiple heaps. It's just a waste.
Okay, he says heaps can be very large and duplicating them or making n of them would be a waste. Okay, that's one way, that's true. What's another reason? Yeah?
Maybe you actually do want both threads working on the same object.
Okay, she said maybe you do want both threads working on the same object. The threads often, not in my prime number case, but threads sometimes need to, often, most of the time, threads need to communicate with each other. They're collaborating on some task. Maybe they're updating the same list. Maybe they're each off calculating stuff, and as they find something, they put it on a list. So you can write it so they're both adding to the same list. So they need both access to the same list or they can't do their job, but you've got to be careful well, what do you have to be careful of? If they're both writing to the same list, yeah?
Synchronicity.
He said synchronicity. Wasn't that That's an album name. Anyway, what's synchronicity mean? We got this thread writing to a list, adding to a list, this other thread adding to a list. What could go wrong?
Wrong order.
They could interfere with each other. Right? If they're both changing the same instance variables at the same time, chaos can ensue. So you have to synchronize these threads. Typically what you do is there are constructs that you'll say, this method can only be executed by one thread at a time. So if one thread is busy adding to the list, the other thread isn't able to add until the next other thread is finished. So you have to coordinate. You have to, yeah.
If you don't do these kind of like, make sure they're not doing the same thing at the same time, the errors that will result, will those errors inform like where it'll run great 99% of the time and then 1% of the time it'll just happen to hit?
That's the frustrating thing with multi-threading. That's exactly right. Suppose you didn't take care. You just let the two threads add whenever they wanted to. Well, the adds don't take long. And so it might be extremely rare that both threads will be trying to add at exactly the same time. But, so your program might run fine this time, and you decide it works. And then you, next time it doesn't work. So suddenly it becomes a little bit indeterminate about whether your program is correct or not. So testing is no longer sufficient. You need to also be able to reason about the parallelism that's being used. You have to be able to think about your program. Yeah?
So when you say maintaining thread state in memory, does that mean like a RAM, like a temporary memory?
Yeah, I'm talking about RAM.
Okay.
Yeah, the stack is in RAM, and it moves into the cache and moves into registers. But so they share, there's a piece of memory that all the threads for a program use. Part of it is used for stacks for each thread, and they have exclusive access to their stacks. The rest is for the shared access to the code, and then the shared access to the heap. So let me pause in this part and go back and show you another programming example. This one is called synchronization. So that was a good word he picked. So the main method, I'm creating a new sync object and calling compute of whatever, 10 million or something. So we are in the sync class. So there is an instance variable, a property called total that you can get or set. Let's look at what compute does. Compute fires off two tasks. One runs the increment method, and it gets in as a parameter, say 10 million as a parameter. The other calls a decrement method, and it gets in. It gets the same number as a parameter. And then we start both tasks. We wait till they're both completed here. And as soon as they're both completed, we write out the total. Now, I think that both of those threads will have access to that variable right there. Or both those tasks. Why? How can we conclude that inside of increment, I'll be able to access total, and inside of decrement, I'll be able to access the same total? Yeah?
Is it because it's in your heap or something?
Well, it's in the heap. I mean, where's this object sitting? It's sitting on the heap. We did a new somewhere to create the object, so it's sitting on the heap. But why does increment have access to total at all? It's basic. This isn't meant to be a difficult question. Here's increment. Here's decrement. Why do they have access to total? Yeah?
They share the same copy of code?
No, it's not that they share the same copy of code. Yeah?
Because they both the instance methods refer to
Yeah.
the same instance.
They're both non-static methods, so they have access to the instance variables of the class. That shouldn't be surprising. So compute, increment, decrement are all methods in this class. Of course they have access to that property right there. Furthermore, When we run increment, that's really shorthand for this dot increment, and this is shorthand for this dot decrement. Those methods are being run on the same object. So they have access variables to the, they both have access to the instance variables of that object. So, you remember, this is the implicit parameter. The reason they can share access to the same piece of the heap is we're passing the same implicit parameter to both of them. They can both access the heap via this, and that, in both cases it refers to the same chunk of memory. So they're both able to modify that variable. So remember, we call, this task is running increment 10 million times. This task is running decrement 10 million times. So look what increment does. Ignore what I've commented out. What does it do? Not a hard method.
Yeah.
Someone's got to be able to be brave enough to say what it does.
Increments it 10 million times.
Right, it increments total 10 million times. That's all it does. And here's decrement. It decrements total 10 million times. And let's go back up where we call it. We call it, you know, we start the task, we wait till they're done, and we write out total. Total starts out 0. It ought to end being 0, right? If we increment it 10 million times and decrement it 10 million times. Okay? Let's see what happens. Oh, I'm running the wrong program. Oh, I want to run Synchronization. Okay, there we go. Now what the main thread is doing is every half a second it prints out the current value of total. So what happened was after half a second, increment was winning. After a second, increment was winning. Increment was still winning. At some point, decrement started winning. Then sub finished, and then add finished. I don't know exactly how long it was between these prints. But when it was all done, the total was 29,117,669. So that must be 100,000 or a billion or something I passed to it, not 10 million. It's not 0. All right, remember that number. Minus 291 million. Let's run it again. It's positive by a lot. What's going on? Why do we get a different answer? Or why do we get a different answer at all? Yeah?
Because one thread is claiming control over it and probably blocking out the thread.
Well, okay, he's saying one thread's claiming control and blocking. In fact, the problem is there's no synchronization at all. So these two threads are just running flat out, repeatedly incrementing the shared variable. Well, what's involved in incrementing a variable? You look at it and you see one instruction, right? Variable plus plus, or variable minus minus. What's involved in doing variable plus plus? Yeah?
Read it, add one, write it back.
Right, 3 steps. Read the variable, you know, get the value of the variable, add 1 to it, store it back. 3 things. Decrement, read, decrement it, put it back. Now, if the two operations were arranged so that we could not be incrementing and decrementing at the same time, things would be different. What can go wrong now? Yeah?
Additions and subtractions can cancel out.
Okay, well if they canceled out, we still ought to get 0.
Yeah.
Think about it this way. Suppose the value of the variable is 0. And imagine that the two threads are running in perfectly at the same speed. Okay? So both threads simultaneously get the value of total. So they both have 0 as a value of total. One thread adds 1, so it has a 1. The other thread subtracts 1, it has negative 1. And then they both simultaneously store back to the variable. One's trying to store 1, one's trying to store negative 1. Okay? Now the truth is, you can't have the way at the level of storing in individual variables, that can't happen at the same time. The process, one or the other, is going to be forced to go first. It can't happen simultaneously just because of the way that the processor is made. So one of them is going to succeed in storing its, let's say the one thread succeeds in storing the 1. Immediately after that, it'll be overwritten with the negative 1. So they're interfering with each other. And it just depends on sort of the vagaries of exactly when things start up and which threads run faster and so on. But you'll get a different answer every time. Okay? So how do we fix this? If the root problem is that the increment operations are happening simultaneously, what do? Yeah.
Make sure that one increment and decrement operation fully completes before something else
Okay.
goes on it.
We make sure that one operation completely finishes before another one can run. So there's something called a lock statement. So what this means is, the effect is, I'll explain more about locks later. The effect of it is that only one thread at a time can be in executing this code right here, or this code right here. You will never have a situation where one thread is in this highlighted region and another thread is in this highlighted region. The lock prevents that. We've given two regions of code. We marked them, they're called critical sections. Only one thread at a time is allowed in either one of them. All right? So now we're forcing exclusive access to this. So if I run it again, right, we'll see that the numbers are popping up and down. Now if I ran it again, I'd end up at 0, but the numbers you see as it's running are different. So I'll run it again. And we're done. Yes?
Is it necessary to lock both methods, or do you only need to lock one because if it locks the other one?
No, I need to lock both. The problem occurs when I have one thread inside of the incrementing and one inside the decrementing. So I've got to force exclusive access. Only one thread at a time per critical section. What else did you notice when I ran this, besides the fact that it ended at 0? Yeah?
It's slower because it's
Slower because of the locking overhead. All that locking and unlocking takes time. So, let's be more aggressive. Let's change it. Instead of saying that only one, you have giving exclusive access to that. What if I said only one of these while loops can run at a time? So now I'm saying only one thread at a time in either while loop. Now what's going to happen when I run it? Much less locking overhead, right? I'm only having to, the locks are only dealt with once. Yeah?
Well, what's the point though, right? Because now it's like it's running on a singly threaded.
Right. I've completely, so I run it, and you'll see, okay, it's a lot faster than the ones where we were doing all the locking. But we're not doing anything in parallel anymore. So I'll just finish by observing, this is a toy example. This is the struggle in parallel programming. You have to do synchronization in some fashion. If you do synchronization, if you do synchronization at too high a level, you sacrifice your parallelism. If you go down at too fine-grained a level, suddenly you're not doing enough synchronization and you get wrong answers. It's finding that balance that's hard. And we'll continue with this next week.